Okay, so welcome back to the Ultra-Scale Playbook series, reporting to you live from the sauna. And as we covered the parallel programming crash course appendix last video, we can now jump straight into data parallelism. And to remind you, what we're doing is we're replicating the model on several GPUs, which we call model instances, and we run forward and backward passes on different micro batches of data in parallel for each GPU, and this is why it's called data parallelism, because the data is flowing in a parallel way. And in this example, which you've seen in the previous video, we have 3 GPUs that are doing the forward and backward pass on the model simultaneously. And then the real crux of this sophistication is these 3 arrows, because this needs to be combined in what we call an all reduce step. So of course, when you have the arrows, it looks trivial, but in practice, there are many ways to have an unoptimized implementation. So this is very important to pay attention to. Let's see what it says here. Using a different micro batch for each GPU means we'll have different gradients in each GPU. So to keep the model instances in sync across different GPUs, the gradients will be averaged using an operation called all reduce. And this happens during the backward pass before the optimizer step. So as it said here, when we finish the last backward pass, we perform all reduce to synchronize the gradients, and then we will update the gradients across the GPUs for the next forward pass, which continues on and on. So this is the first distributed communication primitive that we actually introduced within the series, once again, and it handles the communication and synchronization between GPU instances and nodes. One thing which confused me for a really long time, so maybe you've had this problem as well, is that this graph here only is showing one GPU. So what I first believed that this was describing is the GPU 0, 1, and 2, which doesn't make sense because that means that it is doing it sequentially, which defeats the entire purpose of parallelism. But after talking with GPT with this, at least the only explanation that makes sense is that we have a 3-layer neural network, for example, on each GPU. So the GPU 0, 1, and 2 will do the 3 forward passes and then backward through the 3 layers in reverse order. And then in this step, it's synchronizing across all 3 GPUs. So just please note that this is not the device index, but rather the layer for each GPU. And what they're saying here is that a naive data parallelism implementation would wait for the last backward pass to finish, or the last backward layer to finish and the entire backward pass, so that we can synchronize and average with all reduce. However, this is a big no, because we don't want our GPUs to stay idle while communication is happening, like on the above graph, which means that in our computation timeline, once the communication is begun, we are wasting our GPUs on a lot of idle time before the optimizer kicks in and updates the gradients, which is, as we can tell, very unoptimal. Okay, and now we're going to go through 3 optimization strategies in this video to improve from this naive implementation that will build iteratively from each other. So the first one is called overlap gradient synchronization with backward pass, and it's maybe the first thing that would come to your mind intuitively. So the naive distributed data parallelism approach that we're using is naive because we have to wait for gradient synchronization before updating the parameters. But what we're asking here is, could we overlap this communication with our computation? And the answer is yes. So for example, as soon as the backward pass of the last layer is complete, which is this layer here, I'm not sure why it's saying last box on the right, it's kind of confusing. There are a few typos in this playbook, so that's worth noting that some things you have to doubt their meaning. Anyways, as soon as this is complete, those gradients can already be gathered and summed while the backward computations continue for earlier layers, moving toward the left. So once again, when we do the backward for early layers, we're actually moving to the right. So perhaps I'm mistaken here, but that's my understanding. In essence, we can start even before the backward pass is done through the last layer of the model. And this is because, I suppose, as soon as we start computing values, every time essentially we call backward, we can begin to communicate these to the other GPUs and reduce them. And reduce just means sum them up and then average them out. So this can be achieved in PyTorch by attaching an all reduce hook function to each parameter. And this approach overlaps most of the all reduce operations within the gradient calculations, which is to say within the GPU computation, thereby improving efficiency. And so that means that this idle time is much shorter than this idle time, even though like in this diagram it's the same length. Of course, in actuality, having to calculate or having to synchronize only like 1/3 of the middle layer and the entire first layer instead of all 3 layers will evidently be faster. Okay, and this is just the simple hook to register all of the parameters that require gradients, and that's why we have if p requires grad is true, and we just put this parameter, we add this hook to the parameter such that it will perform an all reduce every time that we call the backward function. In summary, overlapping computation and communication reduces the time spent waiting for gradient synchronization across the entire model, and gradient synchronization can occur at least partially in parallel with the backward pass, which means that we can combine computation and communication, which will significantly speed up data parallelism. GPT was quoting like 1.36x speed up, which is non-trivial. And there are also these implementations in Pictotron, but for this video, I'm going to skip that. Feel free to go to the website and interact with these, because with the PDF, of course, this is not interactable. And so this is an example of overlapping communication and computation and communication, but this will be discussed more and more as it is an essential technique to maximal scaling efficiency. Now let's move on to the second of three optimizations, which is called bucketing gradients. And this one is definitely more intuitive. So GPU operations are usually more efficient when performed on large tensors rather than having many operations run on small tensors. This is also true for communication. Thus, we can advantageously group gradients into buckets and launch a single all reduce for all the gradients within the same bucket, and each bucket being a layer of the model, instead of performing independent all reduce for each gradient, which is this case. So for each gradient, we're performing all reduce. Here, we're doing it within the bucket, and you can see it's kind of like a Lego piece that's just shifted by one block, because of course, since we're waiting for the entire bucket, we need to have the entire gradient calculation completed for the backward pass on layer 2 before we can begin to all reduce and communicate through the 3 GPUs, at least if we use the same example as before. And they have an excellent analogy here. So it says, think of it like packing items into boxes before shipping. It's more efficient to send a few big boxes than many small ones. By performing a single all reduce operation for each bucket, we can significantly reduce communication overhead and speed up the communication operation. So pretty intuitive. And if you're once again interested in seeing more, you can check out the bucket DP implementation in Pictotron. The third and last optimization isn't as obvious because we're actually adding something. So we initially added data parallelism in order to mimic gradient accumulation, or rather have gradient accumulation happening parallelly, right? Because when we do gradient accumulation on a single GPU, this means that we have to do one batch, second batch, third batch, and then optimize. But if we have it on 3 GPUs, we do 3 batches simultaneously, and then all reduce, and then optimize. But what if we add gradient accumulation to essentially get more free lunch? So as an example, you'd have 3 GPUs, each running 3 batches, and then after 3 batches, you would all reduce. So GPU 1 does 3 batches, GPU 2 does 3 batches, GPU 3 does 3 batches, so 9 batches in total. And then after every GPU has done a third batch, we will do the optimizer step. And there's a very naive problem here, which would occur if you, instead of performing the all reduce after the 3 GPUs, after the 3 batches, do it after every batch. So this is to say the naive implementation would say, okay, each GPU does its first batch, now let's all reduce the gradients and everything. Now we do the second batch on the 3 GPUs, all reduce, and the third batch, all reduce. This is completely unnecessary because what you can instead do is, since you only need the gradients during the optimizer step, which is after 3 batches, you'll simply sum up within the GPUs, so no communication required, only computation, and no idle time. You'll sum up the gradients for the 3 batches and then perform the all reduce. And this is honestly kind of obvious, like why would you essentially consolidate between every batch when you only need it at the end during the optimizer step? So I think I just went through exactly what is highlighted here. And then our last note before I end the video today is that when performing communication operations, tensors must be contiguous in memory to avoid redundant memory copies. And contiguous means literally side by side. So if you think of memory as a grid, contiguous means that you can have one pointer at the beginning of the tensor, and then the rest of the elements in the tensor or parameters will all be sequential. And what this means is that you don't need to have pointers pointing to all of the different points in memory. Like with a normal array, you would have to have one piece for the data and then one piece for the pointer because it's not contiguous. But when it is contiguous, you'll need one pointer at the start, and then you can just literally add 1 byte to get to the next data point in that tensor. So we need to have this to happen. So in order to facilitate this, we often pre-allocate continuous buffers of the size of activations or model parameters specifically for communication. While this speeds up communication, another typo here if you're aware, anyways, it also contributes in part to peak memory usage during training. So of course, if we have to pre-allocate this memory, then because of this, we're gonna have to have a little more memory usage instead of instantiating memory when we need it, but instead having to like search for it in memory and lead to a less efficient memory structure. And furthermore, this also tells you why we need to know the exact activation requirements. So if you've watched episode 1, it gives you the formula, at least for a transformer, of knowing, given the amount of parameters, given the size of the transformer, how much activation memory is required during the training step. And if we know this, then we can better optimize our memory allocation at the beginning of the training run. So there you have it for our video about the 3 optimization steps in data parallelism. Tune in for episode 5.